where V1 and V2 are those two voltages, and also to solve for Ix, whereas Ix is this current, using the nodal analysis technique. So the first thing you're going to look at is recognize the nodes in the circuit, and we know that this is the reference node, which reads 0 volt in reference to any other nodal voltage in the circuit. Then we have V1 and we have V2. And if you look into the circuit, what we realize is that there is a voltage source. There is a voltage source, which is this voltage source, the 20 volt voltage source, between two non-reference nodes. And this is a problem. And let me show you what kind of a problem do we have here. For example, use KCL at V1 using the nodal technique. We can define the current going through this resistor to be V1 over R1. We know the current leaving this branch, which is the negative 2 milliamp, but we don't know what's the current going through this voltage source, because we don't have any relationship that describes the current going through this voltage source. The resistor's current is defined by Ohm's law. The current source is basically the current going through the circuit, but the current through the voltage source is not defined. Also, the same story applies if you go to node V2. At node V2, we know the current through R2 is defined by Ohm's law, so the current going to be V2 over R2. The current leaves here going to be the 3 milliamps, but we don't know what's the current going through the voltage source, because there is no direct relationship that describes how much current will leave or enter the voltage source. We know what's the current will leave or enter the resistor, or the current defined by the current source, but we don't know what's the current going through this voltage source. There is a trick around this particular problem, which has to deal with something we call the Gaussian surface. So assume that this is a Gaussian surface. So a Gaussian surface is nothing but a balloon, right? So it's a balloon and you have a surface around this balloon. Now, so this is called the Gaussian surface, right? So this surface or this balloon will have currents going into this surface or this balloon. So there is current going in. This current going into this surface or this balloon should equal to the currents leaving the surface or this balloon. That is the basic definition of KCL, is the current enters the surface will equal to the current leaves the surface, but this surface can shrink down to a point that defines a node. Then the currents enter a node will equal to the current leaves the node. If there is no current enters the surface, but all the currents leave the surface, then the sum of all the currents leaving gonna equal 0. It's basically KCL. So the trick around it is to combine the two nodes using the Gaussian surface. So think of a balloon that combines the two nodes. So a balloon that will include the entire two nodes, like shown here. Then we call it a supernode. We call it a supernode because it combines the two nodes. Now the problem becomes much easier because we can sum all the currents leaving the supernode will equal 0. We're going to use the supernode when a voltage source is located between two non-reference nodes. If you have a voltage source located between two non-reference nodes, use the supernode. And the supernode basically combines the two nodes into a supernode. It combines the two nodes and put them within or inside a balloon. We call it a closed surface. It's a closed surface or a closed balloon. So the supernode has two equations. Let's look at the two equations for the supernode. So the first equation for the supernode will use KVL. Well, we know that the voltage will increase from 0 to V1 will equal to V1 here. And then there is a voltage drop across the voltage source here. And then the voltage will drop across V2. So you can use KVL around this loop, for example, to define the supernode voltage equation, to define the supernode first equation. But basically, if you're going to say that if this is V1 and this is 20 volts and the plus polarity over here, right, and this is V2, right, then clearly is that V1 will be bigger than V2 by 20 volts because the minus polarity is here and the plus polarity is here. If V2 was 10 volts, V1 is going to be 30 volts, right, because you add 20 volts to it. So the way you're going to write the equation is very straightforward. You're going to look at the plus polarity of the voltage source. You're going to say that this will be this voltage minus the nodal voltage at the negative polarity. So it's going to be V1 minus V2 equals to 20 volts. The difference between the two nodes is 20 volts. That's the basic idea, right? So you're going to say that V1 minus V2 will equal to 20 volts. You're going to look at the node where the plus polarity is connected. That's going to be V1 minus the nodal voltage where the negative polarity is connected. That is going to be V2, and that will equal to 20 volts. So the equation going to be V1 minus V2 will equal to 20 volts. That's a very straightforward equation. This is the first equation of the supernode. So V1 minus V2 will equal to 20 volts. The second equation of the supernode equation is basically to use KCL at the supernode. So you're going to sum all the currents leaving the supernode equals 0. But something you need to pay attention to is the current leaves here, this resistor for example, going to be V1 over R1. But the current leaves this resistor going to be V2 over R2. So basically what that means is use V1 at the V1 side and use V2 at the V2 side of the supernode. So even though the currents leaving equals 0, you still need to make sure that the voltage here going to be V1 and the voltage here going to be V2. That's the basic idea behind the supernode. So the current leaves this resistor going to be V1 over 5K, plus the current leaves this branch, which is minus the current going in, so it's going to be minus 2 milliamps. Now we move to the other side of the node, so now we are at the V2 side, so the current leaves R2 going to be V2 over 2K, and then the current leaves this current source going to be the 3 milliamps. The sum of all the currents leave the balloon, the supernode, going to be 0. So all what we have to do now is combine the V1 terms and the V2 terms and then take the other values to the other side. But before we do that, we know that we have 1 over K here and milliamps, 1 over K here and milliamps. We know K means 1,000 and the milliamps means divide by 1,000. So if I multiply by 1,000 on the top, this will cancel the K here. And if I multiply the milli times 1,000, that will be 1 because milli is divided by 1,000. So basically we can cancel the K's and the millis by multiplying by 1,000 both sides of the equation. So now when we combine the terms, we're going to have V1 over 5, which is nothing but 0.2 times V1. Then we're going to have V2 over 2, which is nothing but 0.5 times V2. The minus 2, when it moves to the other side, becomes plus 2. And the plus 3, when it moves to the other side, will be minus 3. So 2 minus 3 give us negative 1. This is the second equation for the supernode. We only have 2 equations and 2 unknowns in the circuit. Now we can solve for V1 and V2. So we can put those 2 equations in the matrix form. And from here we can solve for V1 and V2. In this circuit,
V1 was 12.8571 volts, and V2 was negative 7.1429 volts. Clearly that if you're going to subtract those two voltages, like V1 minus V2, if you take V1 minus V2, you should have the 20 volts, right? So one way to check your answer is to go back and plug in those values into equation 1, and the difference between V1 and V2 should be indeed 20 volts. So the only thing left now is to solve for Ix, which is the current through the 5 kilo ohm resistor. So by definition, Ix going to be V1 over 5K. So we're going to say that Ix will equal to V1 over 5K, and that is going to be 2.5714 milliamps. So we have solved for a new type of nodal analysis problem, and this particular circuit has a voltage source between two non-reference nodes. And when you have that, like we have the 20 volts in this case, you're going to use the supernode technique. And the supernode technique says that the voltage difference between the two non-reference nodes going to equal to this voltage source, which is the 20 volts. That was the first equation. And then we use the supernode that combines the two nodes, and we sum the currents leaving the supernode equal 0.